prior to now, if we wanted to prove two things were congruent, we would have to prove every single side and every single angle of the two figures was congruent in order for us to say that the figures themselves are congruent. So it takes a lot of time and a lot of effort. So for triangles specifically, there are some shortcuts. So what I have here is I have 3 things. Okay, so I'm counting this as 1, 2, 3 things. I'm going to make a triangle out of those 3 things. Okay, so we make them come together. Kind of a crude triangle, but it's a triangle nonetheless. So then I have 3 things of the same length. So these 2 are the same length, these 2 are the same length, these 2 are the same length. So no matter how I put them together, maybe I want to try to be clever and I put them together in this order instead. But when I put them together, even though I put them together differently, the triangles themselves are the same size and the same shape. So they have the lengths of the sides are the same. And if I were to take this triangle and I would turn it and flip it, it would be the exact same triangle as this one. Okay, so what I'm saying here is, in order to prove that 2 triangles are congruent, I don't need to have 3 sets of sides and 3 angles. I can do it with just 3 sets of sides. Okay, so that's what we're focusing on today. Let's slide this out of the way here. So we have a new postulate called the side-side-side postulate. And the side-side-side postulate is used to prove, specifically, triangles congruent to each other. So it doesn't do anything else but prove 2 triangles congruent. And we're going to use that later on to prove special properties of things like rectangles and rhombuses and trapezoids and kites. So we're going to use this later on down the road, but we first have to just figure out how to show 2 triangles are congruent. So if the 3 sides of this triangle are congruent to the 3 sides of this triangle, then I can say that the triangles are congruent to each other by side, side, side. Okay? We're going to practice that by just looking at some pictures and see if the triangles are congruent by side, side, side. So my first set of pictures here shows triangle ACB and triangle CAD. The side lengths of the triangles are 3, 7, and 9. So my side lengths here are 3, 7, and 9. Is that equal to the side lengths of the other triangle, which are 4, 7, and 9? So since my other triangle has different side lengths, being 4, 7, and 9, those are not the same. So these are not congruent to each other. Okay, so if we're looking at numbers, the numbers have to be exactly the same for you to say that they're congruent by side, side, side. Okay. The second one does have a single tick mark, so those are the same. Double tick, so those are the same. And triple tick, triple tick. So yes, those are congruent by side, side, side. Side, side, side postulate. And I threw this third one on here because I want us to know that not all of the sides have to have a marking, especially if it's a reflexive side. So I've got one set of sides here congruent. I've got 2 sets, my second set of sides here. And then this side doesn't have a marking, but this side AC, the top triangle, is the same thing as side AC in the bottom triangle. So if I were writing a proof on this, I would say AC is congruent to AC. And if you are staring at yourself in the mirror, you'd be looking at your reflection. So that's our reflexive property of congruence. So if I was doing a proof, this is not asking you to do a proof, but it would be AC congruent to AC by the reflexive property. Then I would be able to mark this with some tick marks, and then I would be able to say, yes, the triangles are congruent by side, side, side. Okay. If I was using a little bit more of a complicated picture, so we've got one more. The picture is just a little bit crazier 8 and 2, not quite 2 because it's 2 plus this little bit. Okay, so I have my side lengths here for this one are 10, 8, and 2 plus whatever BF is. That's my first triangle. My second triangle has side length 10, 8, and it also has 2 plus BF. So 10, 8, and 2 plus BF. So those are the same lengths. So those are the same by side, side, side. Does that mean to write a congruency statement? So we'll practice that one time. The triangle congruency statement here would be triangle ABC. So that first set of triangles, remember, it does not matter your order. You can throw them down however you want. That doesn't affect anything. But now when you do your second triangle, here's where it matters. So when I go down to write my first letter, the first letter that I write in the second triangle needs to be the spot that's the same as A on the other triangle. So A is this angle here that's in between the 8 and the 10 sides. So the angle over here between the 8 and the 10 sides is angle D. So that has to come first. Angle B is the one up top here. So that's going to be congruent to angle E in my black triangle. And then we'll go with the last one, F. So there's my congruency statement. Okay, now let's actually go through the process of writing a proof. All right, so these proofs are going to be pretty straightforward, pretty simple, because we are dealing with our very simplest congruency type, which is side, side, side. So we're going to start with the given statements. Now you'll notice that there are no given statements actually written on the paper, and I don't like it when they do that. However, it does say use the given picture. So the given picture has given markings on it, so we're allowed to say that AD is congruent to this other side. No technicality, since A came first over here, then C should come first on this one, CB, but you can put it the other way as well. That's given. I'll do my other given statement, which is AB. That's a double tick mark on there. Congruent to CD, which is also marked with a double tick mark. That is also on the given. So we're going to go back over that process that we've been talking about several times when we're doing proof. It's that how-to guide that I use. The how-to guide starts by writing the given. Then we use the given. Now, in this particular problem, there's no vocabulary word. There's no bisect, midpoint, parallel, that thing. So we can't actually use the given. So we're skipping over that step, and we're going to get something from the figure. So the figure itself is going to give us a piece of information if we need an extra piece of information. So this one we do need a piece because we only have a set of sides and a set of sides. And I need 3 sides to do side, side, side. So my last side is going to be this reflexive side, BD. So my last piece of information, the figure gives me that reflexive piece because I can see that BD is a part of the top triangle and BD is part of the bottom triangle. Now, all technicality, it should be written backwards for the bottom triangle, but again, it actually even that becomes wrong. You wrote BD congruent to BD. And that is the reflexive property of congruence. You didn't quite see that property of congruence, but there it is, reflexive property of congruence. Okay, now, in my proof, I have a set of sides congruent, a set of sides congruent, and a set of sides congruent. That opens up the side, side, side postulate. And again, the side, side, side postulate only lets you say that the triangles are congruent. So triangle, and I'm going to take this right from the prove statement that's over here on the left. Triangle ABD is congruent to triangle CDB. by side, side, side. Okay. That's a pretty boring proof, pretty straightforward. There's not a whole lot there. So we're going to try another one that has a little bit more interesting piece of information in the given statement. So in this proof, it has a vocabulary word. It has that bisector. So we're going to be using definition of a bisector. So that process, again, that we were using for proofs in the last chapter is still going to be what we use again in this chapter. So step one is that you write the givens. So you use the givens. I'm going to start with BD is the bisector of AC. Now, in our process, we said we write the given, did that, and then we use the given. So the fact that it is a bisector, the definition of that word is going to help us get another piece of information from the diagram. So what I'm going to do is I'm going to write in the second step, definition of bisector. The definition of that word is going to help us figure out what is congruent. The second part of this is that we know that BD, or to read this in kind of a little bit more student-friendly terms, BD is cutting AC into two equal parts. So BD is cutting this line into two equal parts. So the two equal parts of that line are right there. So in my second step, I'll say that AD is congruent to DC. And I have that marked. Now, because I went right into that process of writing the given and then using the given, I missed writing my second statement from the given. So let's get that written down. AB is congruent to CB. That is also given. I'll also make sure to mark that on the picture with 2 tick marks because 1 tick mark is already being used. Okay. So far, I have a set of sides. I need 3 of them to be able to prove the triangle is congruent, which is what I'm being asked to do. So my third piece is after I write the given, I use the given, I can get something from the figure. From the figure, your options are vertical, reflexive, or linear pair. But linear pair, do not bring in 180 degrees unless 180 degrees is already in your proof. That's something that we discussed when we were doing this in chapter 3. So we definitely don't want to bring in linear pair, but I can use this reflexive side right here. This BD congruent to BD, that would help us out a lot to get my third side. There's the reflexive property congruence. And now I'm ready for side, side, side. And the triangle congruency statement that I'm going to write, I can steal right from here. If you'd like to write your own in a different order, just because you're rushing and you forget to look up here, that's no problem. You can write it as long as yours are in the correct order. You don't have to look up there, but it's already done for you. You don't want to have to think that hard. And there we go. The last thing we're going to do is we're going to do a little bit of proof in the coordinate plane. Proof in the coordinate plane requires you to not use any numbers, and we're going to use numbers, so it's a little bit less than actually doing a proof. So we're just going to kind of look at the coordinate plane and see if my triangles are congruent. So I'm going to take these 2 sets of coordinates, and I'm going to go ahead and plot them in the coordinate plane. 1, 4, negative 4, 1. There's my first triangle. Second triangle is 4, negative 2, 7, negative 4, 10, 0. My question is, are those two triangles the exact same? Currently, you might be able to look at the triangles and kind of see that they're almost the same, but not quite the same. But let's be definitive. Let's make sure that they are or are not the same. So to do that, you could do the distance formula for this side, this side, this side, and then again for this side, and this side, and just show that the lengths have the same number. I think that takes way too long. So you're more than welcome to do the distance formula. I'll even write that here for you. Distance equals x2 minus x1 plus y2 minus y1 squared. So if you would like to do the distance formula, you are free to do so. You are welcome to do so. It will actually help you in your Algebra 2. However, I think because we're in geometry, it's better to use a geometry theorem when you are finding the distances or the lengths. Okay, so in order to do that, let that focus. What I'm going to do is I'm going to make right triangles, and I'm going to use the Pythagorean theorem. So if I want to find the length of this side, I'm going to make a right triangle right here. And I can count the sides of that right triangle. This side is 1 box. This side is 3 boxes. So to find the length of that side, I do 1 squared plus 3 squared equals c squared. That's the Pythagorean theorem. 1 squared is 1 plus 3 squared is 9. So 9 plus 1 is 10. So 10 is equal to c squared. So the square root of 10 is the length of that side. Okay, now when I go to compare it to the other triangle has the side of, I'm going to make my right triangle over here. This is 2, and this is 3. If I were to do the Pythagorean theorem with 2 and 3, would I get the square root of 10? 2 squared plus 3 squared, that's 4 plus 9, that's 13. So I would get the square root of 13 here. So this side is the square root of 13. Those two numbers are not the same. And because they're not the same, these triangles are not congruent to each other. If for some reason I got all 3 of the sides of this triangle and all 3 of the sides of this triangle to be congruent, I could say yes, it's congruent. But if even one of the pairs of sides doesn't match up, those triangles are not congruent to each other. So that's a much faster way, I believe, to do the distances of the side lengths without using the distance formula. But again, the distance formula is right